Okay, so in our unit on forces and fields, I think I can break this up into probably three kind of main things you got to be able to do. Topic one, you have to know how electric forces and fields work. And we've covered that. Okay. There's a whole bunch of formulas involving E and V and Q and K. Okay. So all of the formulas we've covered so far, that would be like section one. Today we're going to talk about magnetism. And basically today's topic is all theory. There's really no numerical backing to this. We're not going to do any formulas. We're just going to talk about like the process behind this. You guys might have noticed on the quiz I gave you yesterday, it was a pretty healthy split of theory to math questions. You're going to get that on the diploma. Like, it's not all calculations. Many of them are like, what would happen in this scenario? Which way is this moving? Or if you triple this charge and make this charge a third as much, what would happen? Anyways, hopefully you know the answer to that one. I don't want to say it out loud. But okay, so that's what we're going to do today. The last thing we need to talk about, topics 6 and 7, are how magnetism and electrostatics, how they relate to each other. Because there's a lot of interplay between magnets and charges. Okay, so electric fields is topic 1, basically. Magnetic fields is today topic 2. And then the next 2 days we're going to talk about how they relate to each other. Sound good? Okay, let's talk about magnets. You guys can read, so I don't need to like read directly off the slide here, but like people have known about magnets for thousands of years. Right? The legend is that a shepherd named Magnes discovered a rock stuck to his shoe. And there came the word magnetic out of his name. I don't know if that's true or not, but that's the legend. Okay. Some of you guys take chemistry. You may or may not be familiar with this compound right here, Fe3O4. It's actually a strange one if you know much about the chemistry charges. This is actually, in case you're wondering, it's a conglomeration of iron 2 oxide mixed with iron 3 oxide. This is iron 2 oxide if you know anything about chemistry. This is iron 2 oxide. This is iron 3 oxide. And if you like merged these together, you'd have 1, 2, 3 irons and 1, 2, 3, 4 oxygens. And so if you mix the two most common iron ores together, you can actually make an iron ore that has magnetic properties. And so, I mean, like I've said right here, scientists like a couple hundred or 1,000 years ago, they weren't really scientists, they were magicians. They would use these as like parlor tricks to like fool the masses into thinking they could do something really magical. Does that make sense? So here's what they did discover. If you took a small sliver of a magnetic rock and put it on water, it always pointed north. Let me say that again. These magnetic rocks they found, if they took a small sliver of it, put it on water, it always pointed north. Nowadays, we have a new name for that. We call it a compass. Okay. So my goal today is to try to talk about the theory behind how magnets basically have these abilities. First thing I want to point out is this term. I'm sure you guys have heard it before. Magnets have poles to them. Like we call them the north and the south pole. This is very similar to electrostatics. Electrostatics, you have positive and negatives. In magnets, you have north and south. That's all, right? And we designate them with those words. I mean, we just chose north and south, but I mean, they could have honestly been any words we wanted to. We just chose them based on geographically what we call things. Okay. So I've got a picture here. We're actually going to do an activity like this later on, like next week. This would be a good example of what a magnetic pole field line drawing would look like. Underneath this, you basically have a bar magnet. The way a bar magnet works is like, usually they make like one half of it like say red, and like maybe the other half they might color in blue, just so you can kind of see the two different sides. And it really doesn't matter which one is north or south, but like, you know, this side here could be north and this side here could be south. And the basic idea is that the field is always pointing towards one of the poles, right? Take a look at any of these little grains right here. Like right here, it's pointing in. And right here, it's trying to point that way. And right here, it's trying to point that way. And the same thing here, right? Any of you guys have fridge magnets? Right. I mean, how is this different than like, here is my refrigerator, here's my fridge. What does the fridge and the magnet want to do? They want to stick together, right? So just like electrostatic things have fields, so do magnets. And we already know some stuff about magnets, right? Like if they're going to emit a field, fields can lead to forces. Is the field the same thing as a force? No. A field is like what it would do if you kind of let it go, right? Like if I had an object right here, what would it do? It would want to get sucked towards there, right? A force would be like how much oomph it has, right? So they are different from each other. One more thought here. It does depend on distance though, right? Just like with electrostatic forces, if you had a magnet that was like 10 feet away from your fridge, is it going to get sucked into the fridge? Not unless it's like a super powerful magnet, right? So distance still matters. Okay. And you guys probably already knew this. North poles will attract, no, this is wrong. This is wrong here. North poles do not attract other north poles. North poles attract south poles and repel north poles. This is why it's good to read through my notes. Does that make sense? Like things attract each other. No. Like things repel each other. Opposites attract. Okay. So I'm going to give you guys some magnets to play with one day, so you can kind of test this and go, oh, look, these ones are sticking together. These ones are repelling each other. I cannot imagine why this would come up, but just so you guys know, these are the 4 most common ferromagnetic elements. Ferro is like the Latin prefix for iron. Iron is not the only thing that's magnetic, but it's probably the most common thing that you can magnetize. But you can also magnetize cobalt, nickel, and gadolinium. Most other metals are not nearly as good at being able to be like magnetized, but they could. I don't have any plans to test you on that, by the way, but in case it comes up. So here's what I need you guys to be able to do, and I can almost guarantee this is going to be a test question on the diploma. Every year they send out to teachers like some guides for like what to prep students for, and they have strongly suggested the last couple of years that you guys should be ready for a Venn diagram. You guys know Venn diagrams that kind of look like this? They're going to ask you to basically be able to tell you what is the same between a electric field, which we use E for, a gravitational field, which we use G, and for field here, basically we're going to use B as the letter for magnetic field. And you guys should be able to tell me some similarities and differences between electric, gravitational, and magnetic. So let me go through some of the examples on the slide here. Magnetics and electric things are quite strong. I know we think gravity is quite strong, but the only reason we notice gravity is because Earth is so massive. Does that make sense? But really, these two fields are way stronger. Okay. Both of these two use an inverse squared law. They both are very similar. They use like G M1 M2 over R squared and K Q1 Q2 over R squared. That's a similarity between these two. We do not calculate many things in magnetics. There are 2 formulas we're going to learn tomorrow. They're fairly straightforward, but we don't actually do a lot of calculating magnetic fields. So don't stress over that one there. But these 2 you should know that it's all about something being squared in relation to distance. These guys can both attract and repel because you have positives and negatives, or you have north and south. But gravity is only ever attraction. What are things related to? Well, the charges affect electric fields. The masses affect gravitational field. What are magnets affected by? How strong your magnet is. You have a stronger magnet, you have a stronger field. Okay. This is probably the single biggest difference I need you guys to be aware of. In gravitational fields, you can separate the 2 objects. Are you and the Earth exerting gravitational force on each other? Yes. Can I separate you from the Earth? Sure, jump. I mean, you'll get pulled back down, but can you be separated? Yes. Electrostatic charges. Can I move 2 electrostatically things apart from each other? Not with magnets. Okay. The individual poles from a magnet can never be separated. Okay. It's called a monopole, and I've got slides on this later. Scientists are actually currently working on trying to find monopoles because they believe they should exist. If you can separate the 2 things for gravity, and you can separate the two things for electrostatics, why can't you separate a north and a south pole out of the same magnet? Why can't you break a magnet in half and have just a north pole and just a south pole? Here's the weird thing, though. If you break a magnet in half, you just get two smaller magnets. You know that? So scientists are actually working on trying to find monopoles. They predict they will exist. If you watch the TV show The Big Bang Theory, Sheldon was actually working on trying to discover monopoles in an episode once. And I've got a note on that. Why don't I go here? I'm going to skip a slide. I'll come back. So, modern theories predict that we will eventually find monopoles. They believe that somehow we're going to find a way to take a north and south magnet, cut it in half, and only have a south, only have a north. But like if you did cut this magnet in half, as far as we've ever been able to tell, all it's going to do is just make two smaller magnets. Rip it in half again, now you got three magnets. Does that make sense? Let me go back a slide. Sorry I'm making you guys flip everywhere. Since I was talking about monopoles, I thought I'd find that information there. I need you guys to know that there are three main ways that we make magnets. And you're probably familiar with these. Again, we're gonna do an activity where you play around with them. Here's the three main ones. Here's a bar magnet. And literally what will happen is on one side you'll have a north pole, on one side a south pole. That's a pretty common one. This refrigerator magnet is similar, except the way it works is that the top, let me change the color here. The top side would be north, and like the bottom side would be south. So like opposite sides of the button are your north and south pole. Cut it in half, you still have a north and south pole. And then this is your typical horseshoe magnet. Okay. And the same thing occurs here. One of these sides would be north, one would be south. And it goes like in a U shape. I have some of all of these, and so we'll play around with them. We'll try them. Any questions? No. Okay, so back to this. Let's talk about why magnets work the way they do. If we're talking like 2,600 years ago, back when like the first guy gets a rock stuck to his shoe and he's like, what's going on? We know more now, okay? We're able to look a little bit closer. And it has to do with something called domain theory. You guys can see how that's bolded on my slide there. I'm gonna just kind of hop right to the picture. Most materials, if you were to kind of look at the orientation of like different particles within them on a zoomed in level, they would be mostly randomly scattered. Like this one would be pointing this way, this would be pointing that way. They'd all be pointing different directions. But when something is magnetized, they all point in the same direction. Everything is aligned. That's the key word I've got right here. If stuff can become aligned, it can actually like magnify those properties. Because what you really sometimes have is a small north and south pole and another small north and south pole. Like all of these little arrows right here are like small little poles. Okay. Some of you guys have taken chemistry. I've asked this before, right? You guys have heard of like maybe polar molecules before and how polar molecules have the ability to stick together? It's the same sort of concept. If you have these smaller little sections, these domains, if they're all lined up in the exact same way due to polarity, well, you have a magnet. Does that make sense? But if they're not, like this desk right here, there's probably all these little sections there, and maybe there's some polarity in there, but like it's all randomly scattered, and it looks neutral. Okay? But line it all up. Does that make sense? So the concept I want you guys to know is it's similar to induction. Remember how you brought like the one wand close, and it caused a separation of charge, right? We can make all the positives go one way, and all the negatives go the other way. It's kind of like that. Bring a magnet nearby, and you can cause all of these domains to line up perfectly. Okay. So I like this kind of picture here. This is the domain theory, basically. This is like this is meant to be like a piece of metal. This slab of metal is currently unmagnetized, and it's got all these different poles that could be aligned if we want them to, and they're currently just all randomly wherever. Right? Stuff is polar. But you magnetize it, well, now it amplifies everything. Fair enough? Okay. This explains why monopoles are hard to find. Because let's say that you cut this thing in half. Right there. This was the north side. This was the south side. Let's say you cut it in half. Well, what is a magnet? Well, it's really the sum of a bunch of smaller, littler magnets. You know what I'm saying there? So if you cut it in half, well, there's still all the norths are still on this side and all the souths are on this side. You just made yourself two smaller magnets. So now I don't actually know how they're attempting to find monopoles, because I got to be honest, if I had the answer, I would win the Nobel Prize that year, guaranteed. You know what I mean? So I don't know how they're going to calculate, how they're going to solve this, but they do believe they're going to find a monopole one day. Okay, some more terminology I need you guys to know. If the domains get locked into place, they're permanent magnets, and there are certain things that just stay magnetized all the time. Those are like your fridge magnets, right? They should always stay magnetized. Now, over time, things can become demagnetized. The two most common ways you can screw up a magnet, you drop it or strike it. Okay? Long story short is if you add energy, it makes it so that all of those domains no longer go in a nice even line, and if they kind of scatter around, it kind of slowly but surely demagnetizes. Okay. The other thing you can do is you can heat it up. Heating things up makes electrons move, but if electrons move, then that also screws up the alignment. Okay. There's something called a Curie temperature, named after Marie Curie. We're not going to utilize this because we don't do the math on it, but just so you know, you can actually make a magnet stop working if you heat it up. Because what ends up happening is once it reaches a certain temperature, the electrons are vibrating so fast that they're no longer in this nice aligned pattern, and they're now looking more like this one here. Right? So you ever need to break a magnet, heat it up. Okay, one of the things we're also going to work on, and that you're definitely going to get theory questions about, though, is something called the temporary magnet. Okay. And I'm going to show you, not today, sorry, we're just going to do things in sections, but I'm going to show you how we can actually make something called an electromagnet. Anyone ever heard that phrase before, electromagnet? Where you can make a magnet that you can turn on and off with a switch. Okay? They're quite useful, actually. We'll get to that another day, though. Like I said, today is mostly just like terminology and theory. We'll do the math part another time. Okay, this slide right here, I want to talk a bit about magnetic field strength. I already mentioned this earlier. The symbol you're going to see is the letter B. I don't know why we went with B. I'm assuming it's because M has already been used for mass, so they had to pick like a different letter. But if you ever see the letter B in a formula, that is your field strength, and its units are Teslas, named after Nikola Tesla. And I've got a couple of notes on here that you guys can read, just so you're aware of like how strong certain fields are. A fridge magnet is about 1/100th of a Tesla. Earth is actually a very weak magnet. Strong magnet in our lab would be 5 Teslas, and a star is like 1 billion Teslas in terms of how magnetic our sun is. So a couple days ago, I would have talked with you guys about V for voltage. And there were a couple other words for voltage you could use, one of which was potential difference. These were synonyms for each other. I need you guys to know there's actually more than one word you might come across when you talk about how much magnitude you have. The words you might come across are magnetic flux density or magnetic induction. I don't believe I've ever seen a question on that, but like in case I ever ask you about like a flux density, we're talking the same thing. Okay. And it basically has to do with like how much torque a compass needle would have. Okay. The more that it like zips to try to like align, the more force you have, then the more Teslas you have. That's like the way that we define it, right? So imagine that there was like a north end of a magnet right here, and we had a compass right here. Let's say the compass was pointing that way. Actually, let me change that. Let's not make that a north magnet. Let's make this one a south pole. Okay, so there's a magnet right here, and the compass was pointing this way. What's the compass needle going to want to do? Yeah, well, it was pointing north, but if you bring a magnet nearby, it's going to want to point that way. Does that make sense? Because that's what the field of the magnet is going to force it to do, right? And so based on how much torque you can have this needle rotate, that's kind of where these words came from, flux density or magnetic induction. Ooh, we've got slides on that, actually. It could be, but no, actually, I've got slides on that. But actually, when we talk about the North Pole, it's actually the South Pole. Yeah, I got slides on that in a bit, though. Okay. Okay, last couple thoughts. Let's get to that, because that's actually the main focal point of my lesson. This is what a Tesla is, a T. In theory, all of these are equivalent to a Tesla. It's insane that you'd have to memorize them all. So please don't worry about knowing them. But like a Tesla could be a Newton per amp meter. It could be a Weber per meter squared. I don't even know what a Weber is. It could be a kilogram per amp second squared. So long story short, the letter I'm looking for is always going to be T if we're talking about a field. If we talk about a force, what do we measure forces in though? Newtons. Okay. So when we get to the math, which we're not doing today, but when we do eventually get to math, if I give you Fm, that'll be a magnetic force. That will be in newtons. If I ever give you a B, which is the field strength, that will be in Teslas. These two things are similar to each other. They are not the same though. One is a force, and one is a field. Sound good? Like I said, though, we're not doing any math on this yet today, I don't believe. You will almost certainly be asked multiple questions where they're going to give you some magnets, some fields, and they're going to ask you, like, which direction are things traveling or which way are the field lines going? And so that's what most of my remaining slides are about, is how field diagrams would work for magnets. Okay. So here's what I need you guys to know. Magnetic field lines are always drawn towards the south and away from north. Basically, the idea is it's what a compass would do. Compasses actually point south, which is weird. I got to explain this in a bit. But if a compass is a small magnet floating on water, the compass has a north pole this way and a south pole this way. The north pole actually gets attracted south. The north pole is actually the south pole. And I'll show you that in a bit. So when you're drawing these lines, though, always draw the line going out of north and in to south. That's our convention. You know how we had to just choose one and just say that like it was a positive test charge? Your pen explode. Shoot. You can go clean it off if you need, I guess. Okay. You know how we had to pick just a positive test charge for electric fields? We just had to pick one. So we just said, what would a north do? North gets attracted to south and away from north. Okay. So here's another picture then. Let's say you have two bar magnets. Which way would the field be? It would be going away from north towards south. Okay. Technically, what ends up happening is it always curves a little bit around the edges. We'd expect to see it kind of do a little bit more like this around the edges. This picture I found just went straight. But this would be uniform in the middle, and then towards the edges it would curve a little. Here's some more pictures of just generic fields. Let's kind of talk through what they would look like a little bit closer. Let's say you just had a single bar magnet. The way we would properly draw this field then is all of these would be pointing towards the south. Everything would be pointing in towards south, pointing towards south, and all of these norths it would be coming out of. That's how we properly define the field. So what would a north thing do around a north? It would repel. What would a north thing do around a south? Attract. Well, you can see here I've got two norths, right? What's going on in the middle here then? Well, nothing, kind of, right? Because what's going to end up happening is this guy's going to want to repel, this one's going to want to repel, this one's going to want to repel, this one's going to want to repel. In the middle here, you almost have no field. Right? If you put a compass in the middle here, it would not know what to do because it would want to point away from this one, and it would also want to point away from this one. And like, it may actually just spin in circles, to be honest, because it's going to have no idea which way to point. You kind of have like a lack of a field there. Here's a north-south one. How would these lines work? Is it going to go that way or this way? Is it pointing towards north or towards south? Okay, so it's going that way, I guess. Okay. And then the most common one we're going to try to use actually is the horseshoe magnet. And one of the reasons why we like the horseshoe magnet is that inside the horseshoe, there is a really nice uniform field right in here. Does that make sense? Kind of like the two plates for voltages. When you have a perfect horseshoe magnet, you have a perfect field like this inside. Around the edges, there's a little bit of curving to it. This is not a uniform field over here. And really, this isn't uniform, this isn't uniform. Maybe a few lines right here, you could consider that to be a uniform field. But like inside the horseshoe magnet, that's a great uniform field. Are we talking in the middle of a horseshoe magnet, or? Well, it depends on what you do, right? Let's write that one out, because it depends on which orientation it's in. Okay, so I'm going to draw a bigger one here. Okay, so let's make that north-south. So let's say you set the magnet up in this orientation right here, north-south like this. This would want to repel. This would want to repel. It would probably just hover there. Does that make sense? But you know what's probably going to happen is it's going to torque. It's going to like twist, I would imagine. And what's going to happen is that this south right here is going to flip itself like out of the page towards us. Yeah, it would rotate. So you'd have to try to find a way to like maintain it there. But yeah, we can use magnets to actually like cause things to hover. Since you mentioned it here, has anybody ever heard of something called a maglev train? It stands for magnetic levitation. And what you basically do is you build a train track entirely made of magnets, and then instead of wheels, you put magnets there as well, but you reverse them. So that what you end up having is, you end up having it so that like this right here is all north, south, north, south, north, south, north, south. This is your track. And then your train that rides on top, I suck at drawing. You put a magnet the other way, you go south, north, south, north, south, north. And these things repel each other. And so what ends up happening is these things literally will like hover just a little bit in the air. But you know what that does is it reduces friction. And so all you have to do is propel this thing somehow. And there's really only air resistance. There's no like friction between two surfaces. Yeah, this is a really crude drawing. I don't know, probably all around it on all sides. But I mean, that depends on the engineer's choice. Yeah, I don't know nearly enough about that. But yeah, I would imagine I would do it on all sides, right? And just keep it kind of hovered right in the middle. Anyways, okay, here's what UV had actually mentioned earlier. The Earth is actually a magnet. And we've known about magnetic poles for a long time. Maybe I should just go right to this section right here. We call it the North Pole. Why do we call it the North Pole? Because the north end of a compass points towards it. Can I say that again? We called it the North Pole because the north side of a compass points towards it. And that was poorly chosen because we now know that north things actually point south. And just like with conventional current and protons and stuff like that, there are a lot of times in science where someone decides to like go with something, and we've been wrong the whole time, but like it sticks. And so we've never really been able to fix this and just kind of say the other way around. So I need you guys to know that the north magnetic pole is actually in the southern hemisphere, and the south magnetic pole is actually in the northern hemisphere. One more thing I need you guys to know. The magnetic pole is different than the geographic pole. Okay. I need to do a quick geography lesson to make sure you guys get this concept. Imagine this is the Earth. Okay, I'm not really good at drawing, so imagine this is like the southern tip of, let's see, that could be Florida right there. This is Canada here. Does that kind of make sense? That's North America, South America? But it's not actually straight up and down, if you guys weren't aware. The Earth actually has a little bit of a tilt to it. It's actually one of the reasons why we have our seasons, is that there is a 22.5-degree tilt to the Earth that tips it slightly sideways. Okay. The location upon which the Earth spins around, that is actually the geographic pole. So like wherever, like if you can imagine this was a basketball that you're spinning around on your finger, okay, the location that it actually spins on, that's the geographic pole. But magnetic poles are actually in a different spot. And here's the weird thing. They are moving. Slowly over the years, we've discovered that magnetic north is migrating. And so I've got a bunch of pictures to talk about here. Here's the first one. This right here is the geographic North Pole. So this one, along with the corresponding one on the South Pole, that's what the Earth spins on. This is where your compass points. Normally, that's not a problem. We live right about here, let's call it. You can't even see that. there's a different conversation there as well. The northern lights are really not based on. Well, I guess what you're saying, yeah, they're getting like, you mean further south in latitude. Yeah, I would agree with that then. Yeah. Sorry. Anyways, sidebar question. If we live right here, your compass needle is going to point this way towards the magnetic pole. It's not really a big deal for geographic pole. You get what I'm saying? But it really screws things up if you were right about here. If this is you, and your needle points that way, north is actually that way. So the further you get north, the more these discrepancies have a little bit of a difference, because this is where Earth's domains seem to end, and this is what Earth spins on. Okay. Here's a picture I have about how the north magnetic pole has actually been moving over time. Technically, this is not the north magnetic pole, though. This is actually the south magnetic pole. So the slide's been labeled wrong, but the point has been made, is over time, since, 1831 until 1994, we can actually see that where north has been is actually moving slowly but surely. It's kind of weird. Okay. Here's the same thing on the south pole. Again, we call this the south pole, but it's actually not the south pole. It's actually the north pole. We can't change it anymore. It's too late. Everybody knows it is the south pole. But magnetically, it's actually north. You will likely get a question on this on the diploma. The idea of south and north being backwards in Earth. So this is where magnetically south points to, but the true south pole is right here, and that's not even true either, because this is actually the north magnetic pole. We just call it south because we can't convince everybody to change their minds anymore. Okay. Similar sort of concept here. When we talk about field lines then, this is the way the Earth's field would work. Okay. If magnetic, okay, again, this is wrong, but this is like magnetic south right here. And this is magnetic north right here. Okay. How do the field lines work then? Field lines do what a magnet would do. And so a compass would point this way. So all of these field lines are going this way, which is why when you're on Earth, your compass points north. It points north, but it's magnetically south. But we still call it north, okay? And that's confusing. Okay. This one's probably a little bit better. This one actually does it properly. Here it actually does label this as the south part of a magnet rather than the north one. So this slide is actually labeling it the way it should be. And this is probably the best one. This is my last one here. Okay. So what we call geographic north is almost magnetic south. So is everybody clear on the four different terms there? There's geographic and magnetic, north and south. Geographic north and south, that's what the Earth spins based on. Okay? So like if you were to literally stand on the North Pole, as the Earth goes around, you would not really be moving. Does that make sense? Oh, my bad. I guess, yeah, you still be moving as the Earth moves, but you know what I mean? Like as the day moves, you're not moving, right? Geographic north is actually magnetic south, but it's not quite. Due to Earth's tilt, there's a slight difference between the two. Not enough that we normally care. The only time you would care is, again, like if you were right here and you had to go north, that would be very confusing because your compass would tell you to go this way, and north is actually that way. So it really only matters once you get like, well, who lives up here anyways? I don't know. You know what? One more weird thing. Now, I haven't read this in a while, but I do believe I read once that scientists believe that Earth's north and south poles have flipped more than one time in Earth's history. They believe that actually north and south have like randomly just rearranged themselves, like millions of years ago. Yeah, the poles, yeah. And like well, we don't know why because we weren't around back then. We can't track it. But they believe that like north and south have actually flip-flopped once in a while. Sure. Could be, yeah. I have no idea. It's just something I read once. Could be. Mm-hmm. That's true. That's a good point. So maybe internally Earth's core has decided to maneuver. I think it has to do with the fact that Earth has like a magnetic core in the very, very middle of it, and that can probably rotate. Yeah, I know. Yeah. Okay. I think I'm done my notes here. Did anybody have any questions on today's topics? Because we're kind of getting off topic now. Jaden. Basically, if we want to figure out whether something is north or south, it depends on which way the compass needle points. So if a compass needle points towards it, we call it south. That's what we've determined it. So actually, if you guys don't mind, give me your attention for one more minute. I'm almost done here. One of the activities we're going to do, actually, well, here, I'll show you. It's all set up. My washing machine broke the other day, which sucks because it cost me $800. But I got this big slab of metal. Okay. Here's what I've done. I've got some very, very strong magnets on here. Like you probably can't even rip them off. Like they're fairly strong. Okay. And what I've done is I've randomly assigned them. Like I've flipped them one way or the other. The game you guys are going to play is I'm going to give you some compasses, and you've got to figure out whether this is north or south facing up, whether this is north or south facing up. Does that make sense? And so, like, if this is a north magnet, which means the south is on the other side, then the compass needle should point away from this one. Does that make sense? But if this one over here is a south, meaning the north is on the other side, if this is south right here, then the compass needle should point towards it. Does that make sense? So this will be one of the games or activities I have you guys play, and you try to figure out which magnet is which. Because, like, I mean, I can't even get these things off, though. They're so strong. Anyways, I could try to take it and flip it the other way, and then rather than north being up, south would be up instead. So that's one of the games that I'll have you guys kind of do when you play around with magnets. So does that answer your question, though? How do you tell whether it's north or south? Depends on which way a magnet points towards it. You can try taking them off, but it's pretty challenging. Like they're pretty powerful magnets. So, Philip, what was that? Yeah, they're neodymium. Yeah, you've heard of those before? Yeah, they're powerful stuff. Yeah, so. Okay, any other questions, guys? Okay, some passing thoughts here because we got half an hour left today. I kind of expected we'd have some time left over. Few things for you guys to work on now. First of all, if you haven't finished your first assignment, I'd like you to finish that as soon as you can, okay? I haven't given you a due date for it, but like ideally that's the first thing you're working on is some practice questions, okay? The answer key is on the wall. Please mark it yourself. Okay? Please make sure that you actually read it carefully so that like if I told you you needed to include the word induction and you didn't, like be honest, okay? But like at the end of the day, I don't overly care. I just want you to learn, so mark that yourself. 2, we wrote a quiz yesterday. Same thing. Mark that yourself, and on both of those 2 tasks, if you have any questions, come ask me. Okay. The next thing I think you're going to want to work on then is either the second assignment, but like we haven't quite done enough stuff on magnet math yet to really do that. So maybe hold off on assignment 2. I would say work on that lab, that activity we did, where we were in Janae's classroom. We were like using the Van de Graaff. We used pith balls. I would say work on that next. Does that make sense? Does that give you a few things to be working on? I don't have due dates. Okay, I'd really prefer to not. Okay, I mean in a couple days, sure, I'll put some days up on the wall there. But like, I really want you guys to change your mindset of like it needs to be done by a certain day. I just want you to finish it whenever you can and get yourself some feedback. Ideally, the sooner you do this, the sooner you can ask me questions. The sooner I can say, yeah, you're doing it right, or here, let me help you. Okay, and I really, really want to suggest have me mark it before you like hand it in. Okay. Once you hand it in, I'll mark it, and I might give it back and say redo it. But like, I am more than willing to look at it and say, hey, this is perfect, and I'll mark it right then and there. That's a 4. Right? Or I'll tell you, here's some ideas, and I might use some sticky notes and write some ideas on there. But like, please ask me to look over your stuff if you want. Sound good? Okay, so you have half an hour today. Tomorrow we're going to do another lesson, and then Friday is some work time. So that's kind of our week. So if you guys want to scatter somewhere else, you're more than welcome to. That's all I got. Okay. Just need to stop this.